There are these medal awards, and there are, of course, also the recognition for being invited here to give a great plenary. And it's my pleasure to introduce Janne Blichert-Toft. She is an EAGGS fellow, and she will now give us a presentation on the Plumbotectonics model. And so Janne is highly recognized for her work because she has found a couple of isotopes with which she can travel back in time and very deep to Earth. She'll speak to us about isotopes as proxies for crustal differentiation. And just for the students here, it's fun to think about CVs and careers. And I can tell you that Janne, after her PhD in 2003 from the University of Copenhagen, she got herself a Marie Curie grant and started traveling, and she picked France. And once she was there for a postdoc, they just never let her go, and now she is one very important researcher in Lyon at the École Normale Supérieure, and she is also an adjunct professor at the University of Rice. She has traveled a lot, worked a lot with different people, is scarily productive if you look at her papers, highly cited, and among the prestigious awards she has received, I would just like to mention the last one she got. It's from the Danish Geological Society for her contributions to high-temperature geochemistry, igneous petrology, and chronology, the Steno Award, also a very important one that is spent only every 4 to 5 years. So, Janne, we look forward to your presentation. Great that you can be here and talk to us now. Thank you.
Thank you, everybody, for being here, and thank you, Antje, for this really nice introduction. And thank you to the organizing committee of this Goldschmidt in Prague for having invited me to give this plenary talk, even though it's still pretty scary, and giving me the opportunity to talk to so many people today. So when I received this invitation to give a plenary talk, really the hardest part was to decide what to talk about. Because what all of us do each in our little field in geochemistry is really quite specialized, and it's not very easily transformable into a plenary talk in front of such a broad, diverse audience as all of you sitting out there. So I'm not going to talk about my favorite thing today, because that really is a little bit too specialized. And so by that, of course, I mean I'm not going to talk about the lutetium-hafnium isotope system. That's my favorite thing, and of course not the Willamette Chardonnay in these pretty nice wine glasses, perhaps a little bit nerdy, of Al Brandon's. But so instead I will talk to you about something which is almost as new to me as it will be to you today, so please bear with me. But this was something which is definitely broader and that allows me to pull in some interdisciplinarity into this talk and hopefully interest a larger fraction of the audience today. So what I will talk about is how lead isotopes provide a geodynamic background for understanding the assembly of Europe, and with Europe as a concept, as a proof of concept, potentially also other continents and tectonic provinces around the world. I'll talk about what lead isotopes tell us about the decline and fall of the Roman Empire, and I'll talk about how lead isotopes trace war and greed. So most of you, except perhaps the youngest of you, but in that case you can still catch up, may have come across this classic paper from the early 80s and remember it, perhaps for its content, but certainly for its catchy titles of Plumbotectonics, which was a term that was coined to describe lead isotope systematics among the major terrestrial reservoirs. Now, the idea that lead isotopes can help interpret regional geodynamics and geochemistry in such a way as to help us get a clearer perception of geotectonic processes at the continent scale was already back then unique and exciting. But Plumbotectonics was before its time because analytical techniques and capabilities were not yet able to fulfill its early promise. But this is no longer the case now, almost 35 years later. So therefore, I will today revisit Plumbotectonics from a modern perspective and call it Neo-Plumbotectonics. That was the best I could come up with. So what I'm going to talk to you about is what we call the new Lyon database of lead isotopes in European and Circum-Mediterranean ores, and which we believe will have applications to a lot of different fields, hence the interdisciplinary aspect of this talk. And so, but before I show you some examples of some of these applications that we think this database will have, let me first describe its specifics so that you know what's in there, based on which criteria, and how it is constructed. So this is all new, it's work in progress, none of this is published. So first of all, the core of this database is a spin-off from Oxford's Oxalate database. Oxalate is the Oxford Archeological Lead Isotope Database that had compiled lead isotope data up to 2001. So we took that as a starting point and we cleaned it up because there were data in there that we didn't want relative to criteria that I'm going to describe to you next. And then we complemented it by extensive literature data from 2001 and up until today, as well as other data in the past that was not already in the Oxalate database. And the data are from low uranium and low thorium K-feldspars, granites, and sulfide ores, notably galena and sphalerite. We have restricted the database to high-quality, high-precision TIMS and multi-collector ICP-MS isotope data. We have restricted the database to samples that have 204 lead measurements, and as you will see later, this is necessary to allow us to operate in a three-dimensional lead isotope space. We have geolocated every single sample using literature descriptions and Google Earth, sample by sample. And this actually turned out to be a really huge project, especially when you started to get into areas like Turkey, where the alphabet is no longer familiar. That includes Scandinavia as well, but at least I could handle that part. But then the Scandinavian countries, they have their own national coordinate systems that we needed to write MATLAB procedures to translate into a common coordinate system. So this was not an easy thing, and we had completely under-evaluated that aspect, but it's done, and this is absolutely fundamental for this database to have any value at all. At this point, we have over 6,800 samples in the database from throughout Europe, Turkey, and North Africa. Europe includes Scandinavia. We have organized all of these data into an Excel spreadsheet that once it is finished, you can have it. And we have also made a user-friendly Excel spreadsheet that will calculate what we call the geologically and the geochemically informed parameters of the lead model ages, mu and kappa values, and the model thorium-lead ratio, and I'll come back to that later, and that you can have as well. And we are in the process of producing every possible combination of maps based on the raw lead isotope ratio and the geochemically informed parameters, and these we make them with GTM, and these maps will be searchable for correspondence with a specific spreadsheet. And so we hope, or we believe, that this database will have applications to crustal and lithospheric dynamics and tectonics, to the environment, such as soil and air pollution, to geoarcheology, which includes the paleoenvironment, to archaeology, such as artifact provenancing and trade routes, archeometry, and to forensics. And today, during this talk, I'm going to show you examples of crustal and lithospheric dynamics and tectonics. I will show you some geoarchaeology and some archeometry. And I will leave those who are far more competent than myself to explore the use of this database to the environment and to forensics. And now Europe is actually, with its dense coverage, you can see almost 7,000 samples, is a unique testing ground for validating the approach of putting this idea of Neo-Plumbotectonics into practical use, sort of a proof of concept being done on Europe before trying to applying it to other continents and tectonic provinces such as North America, Peru, Chile, Asia, and Africa that are much less densely documented in terms of lead isotopes compared with Europe. And then, of course, lastly, the big question is whether new major dynamic structures will stand out when we put all the many separate lead isotope data sets together into one probably geolocated place. All of these lead data sets that we have meticulously produced over the last many decades. By putting them all into one place, are we going to see some things that we had missed so far, that had gone unnoticed as long as we could not see the big picture? So before we move on into the concrete examples, let me first give you a quick primer in lead isotope chronometry, but I'll keep it very simple for your sake and for mine. And actually, for the purpose of this talk, we don't need to know very much. What you need to know is that 3 elements are involved: uranium and thorium, which are both radioactive, and so those are the parents, and lead, which is radiogenic but not radioactive, and this is the daughter. Lead has 1 stable and 3 radiogenic isotopes, and the relative abundances of these lead isotopes are invaluable markers for understanding sedimentary, magmatic, and hydrothermal processes. So I've given you an example here. Let's start out why not at the beginning of the history of the Earth with common lead shown in gray, and let the clock run for the history of the Earth up until today, or at any time interval that you want. And then you can see that after a certain time, we will have grown in the radiogenic lead isotope ratios, 206 lead that has grown in due to the decay of 238 uranium, 237 lead resulting from the decay of 235 uranium, and 238 lead coming from 232 thorium. And so crustal segments and ores that formed at different times and had different geochemical compositions and histories, they will have different lead isotope compositions. And so that's what we're going to explore for the following. A little bit more of a background. Who is hosting lead in the crust? So we have 2 types of lead: common lead, which is unradiogenic lead, and radiogenic lead. First, common or unradiogenic lead is hosted in the crust primarily by potassium feldspar and by sulfide ores, such as galena, for example. And so these 2 elements, they don't contain any of the parents of uranium and thorium. So that means that at the time that these minerals form and cool below the closure temperature of the lead isotope chronometers in these minerals, we will essentially freeze in the lead isotopic composition at that time, and it will not change during the rest of the time. So in other words, the lead model ages that we are calculating will be the age of the last tectonic event that raised the temperature of the crust to above 550 degrees. And radiogenic lead in the crust is hosted mostly by thorium, uranium-rich accessory minerals, typically uraninite, zircon, apatite, and monazite. And of course, data for these lead isotope data for these kind of minerals or ores, we have plenty of them, but they do not go into the lead isotope database because uranium and thorium are potentially mobile, and we have absolutely no handle, therefore, on the parent-daughter ratio, so we cannot reliably correct for radiogenic ingrowth and get to the lead isotopic composition of these minerals at the time that they crystallized. But this is something that you need to keep in mind for later on when we discuss the various processes that go on in the continental crust. So here I show you the distribution of the samples in the database, first map. And you can see these are all the little black dots, and you can see that there's lots of data everywhere. But what you can also see is that there are areas that is not covered by any data at all. So, for example, sedimentary basins, they don't have granitic intrusions or sulfide ores. So basins such as the Anglo-Paris, Germany, and East Central European basins, they are void of data. But like I said, this is an ongoing project, and we hope to be able to fill these gaps by analyzing periodized fossils and crude oil on the assumption that the lead in pyrite and in crude oil derives from the underlying crystalline basement. So in other words, we're going to attempt to look through the sedimentary pile and access and look into the deeper levels of the crust. Surprisingly enough, a place like Corsica, which has plenty of granites and which is a really nice place to go to, doesn't have any lead isotope compositions either. I don't know why nobody never analyzed that, but we now have those samples and we will quickly analyze them and put Corsica on the map as well. Of course, we expect Corsica to have the same lead isotopic signature as Sardinia, given the common tectonic history of these two pieces of continental crust. The Iberian Peninsula and North Africa is also pretty empty in the literature, but we have recently gotten access to hundreds of granites from both areas, so we will be working on filling out the map for those two places as well, which leaves Romania essentially to go in the field and sample granites and ores, unless of course there are people here in the audience who have that kind of samples that they would be willing to share, and then I would be very happy to get in contact. So what I'm sure you already know, or what you could certainly gather from a couple of slides ago, radiogenic ingrowth by its very nature introduces strong but uninformative correlations between raw lead isotope compositions or raw lead isotope ratios. So in order to explain to you what I mean by uninformative, I here show you a map of the raw 2726 lead ratio. It could be any lead isotope ratio. I just picked this one. Okay? And so when you look at this map, you realize that you don't see any particularly eye-catching systematics, except perhaps from the red in Scandinavia and the blue in Turkey. Nevertheless, traditionally, such maps of raw lead isotope ratios have been widely used in archaeology for provenance, for provenance purposes, but they are not geologically informative. So for our purposes, for the rest of this talk, we will rather look at what I mentioned earlier. We will use what I mentioned earlier, what we call the geochemically and geologically informed parameters of the lead model ages, mu and kappa, and the model thorium-mu-lead ratio. Mu is the model uranium-lead ratio, and kappa is the model thorium-uranium ratio. And by model, I mean that these parameters have been calculated or have been backed out from the time-integrated measured lead isotope ratios. And like I also mentioned earlier, those would be the 204 lead-based ratios. So in order to do this nonlinear change of coordinates from one parameter space into another, we used the reference two-stage model of Stacey and Kramer's and equations published recently by Francis Alberidi. And in this way, we can then transform the raw lead isotope ratios into the geochemically and geologically informed parameters of kappa, mu, lead model ages, and model thorium lead. And so now you understand the necessity for restricting the database to 204 lead isotope ratios. Otherwise, we cannot work in a 3D space as we do here. In order to visualize these data, which I'm going to do in the following slides, we average the data over 0.4 degrees Celsius, and we plot them on geographical maps using GMT. Now, the two-stage model of Stacey and Kramer's is a system of three equations with three unknowns, and I'm going to spare you the details of that here and just say that we have constructed this user-friendly Excel spreadsheet in which you simply enter your measured lead isotope data, and the output will give you the geologically and geochemically informed parameters that you can then work onwards with. And so here, I just want to show you an example of how consistent local values are so that you don't sit and wonder whether somehow we are either biasing the data or the presentation of the data by averaging them over 0.5 degree pixels. We are not. The data are incredibly consistent, and this is just one of many examples. And the last map I want you to take a look at before I move on to the new maps is just this classic basic geological map of Europe that looks incredibly complicated. And this is just to jog your memory about where the major collision fronts are in Europe. The red stipple line is the Caledonian, or also known as the Tornquist line. The green stipple line is the Variscan or the Hercynian, whatever you prefer. And the blue stipple lines are the Alpine fronts. So here you have the first map, and this is the map of the lead model ages. And you can see that it shows strong provinciality. And that the data define coherent and well-delineated age provinces. This is particularly the case for Scandinavia with its Svekophenian and its Karelian cores. the contrast between the Alpine, which is outlined here with the green stipple line, and the Variscan of Northern Europe or Northwestern Europe is fairly sharp. Now, if we disregard a few young ages in the post-Variscan extensional system that extends from the Oslo Graben through the German Eifel and into the French Massif Central, and which has absolutely nothing to do with the Alpine orogeny, then Western Europe looks very little affected by the Alpine orogeny when we look at the data this way. In fact, Alpine ages are restricted to the Bedics of southern France, to the Atlas of North Africa, to the Apennines, and most spectacularly to the broad Aegean and Turkish provinces. Another spectacular or striking observation from this map are those kind of Bordeaux brownish areas here, which are Pan-African domains. So this string of Pan-African domains that stretches across Europe in an east-west fashion. So once we take into, once we correct for the rotation of the Sardinian Corsican block in the Miocene and the Iberian Peninsula in the Cretaceous, then this ridge of a Pan-African domain stretches more or less discontinuously, somewhat discontinuously, from the southwestern Iberian Peninsula through Sardinia, if you imagine that it was further up north at the time, into the Austro-Alpine, and it branches out into the Cadomian block of northwestern France. Now, this isotopic record of an east-west Pan-African ridge going through Europe was a so far unnoticed geodynamic feature of European tectonics that we had not noticed until now, when we have put all the data together into one probably geolocated place. And so these Pan-African domains that looks like holes in this vast Variscan province testified to the accretion of cold fragments of crustal material during the Paleozoic orogeny that was detached from the Gondwana margin and later docked to Northern Europe. And so this is telling us that lead model ages are resilient markers of cold crustal fragments. Now, this is the same data that I just showed you on the geographic map, and here I show you all that data in a histogram instead. And so you can see from this histogram that Europe was, the European continent was constructed during 5 and only 5 well-defined major orogenies: the Alpine, the Variscan, the Pan-African, the Swickifinian, and the Karelian. So in contrast to this complicated geological map I showed you a few slides ago, the construction of the European continent actually looks pretty simple when you look at it in this way. Now, individual alpine events such as the Alps, the Pyrenees, the Bedics, the Atlas, the Aegean do not have sufficiently different lead model ages to stand out separately. So we do not see in a histogram like this the separate alpine sub-events. We just have one big alpine peak, and likewise the Caledonian does not seem to stand out from the Variscan, and the post-Variscan extensional system I mentioned earlier simply does not have enough samples in the database to be represented by a separate peak. And finally, one weak point here is that we all know about the Grenvillian, especially in southern Norway, at about 1100, and there's simply no data in the literature, so they're not in the database. Okay, so it does not show up. So this histogram is showing you that Europe was thermally shaped by 5 super events, and only 5, with the possible exception of the Grenvillian at about 1100. So here I show you the model uranium lead and thorium lead maps. And so both of these ratios show a sharp contrast along what we call the Gondwana front between lower values in northern Europe and southwestern Spain, and much higher value in southern Europe. And this contrast is strong enough that these two ratios are defining coherent, well-defined geochemical provinces. But the boundary between these geochemical provinces cross-cuts the model age provinces. Now, if you plot these two parameters against each other, they correlate strongly, indicating that whatever process is responsible for creating these geochemical provinces had something to do with the behavior of lead. And the model thorium-uranium ratio shows the same kind of pattern, although not nearly as well defined as the uranium-lead and thorium-lead ratios. And here again, you have lower values in Northern Europe contrasted against much higher values in Southern Europe. And when you plot the thorium-uranium ratio against the uranium-lead ratio, or if you like, against the uranium-thorium ratio, well, then you have a very poor correlation, okay, which tells you that there is another process at play here than the process that was responsible for the uranium-lead and thorium-lead geochemical provinces. So at this juncture, let's take a step back and try to summarize what we have observed so far. First order. So the age histogram and the uranium-thorium-lead isotope maps that I've shown you give us a surprisingly simple perspective on the making of the European continent. And lead model ages not only correctly delineate crustal segments, which we all knew about for a long time due to this large body of field work and a large body of chronological work done over the last 50 years, 100 years. But they also, in addition, reveal their distinctive thermal and geochemical properties. So this is an added value. So now, most of the ores in the database, they are hydrothermal, and so therefore represent fluids initially mobilized by regional metamorphism or magmatic intrusions, like I alluded to earlier, implying that the lead model ages of the source rocks of the ores and the feldspars were thermally reset by orogenic events. Like I said, the lead model ages is the age of the last tectonic event that heated the crust to above the closure temperature of the lead chronometers in these minerals. So the lead model ages therefore map thermal overprinting and record the time of reheating of the crust to the 350 and 550 isotherms, those of the common lead, the main common lead carriers in the crust. So how do vast expanses of continental crust turn into geochemical provinces the way we have seen it? So the uranium-lead and the thorium-lead maps and the uranium-thorium map, they give us some pretty strong clues to what is going on. And two processes are going on, and they're not mutually exclusive, and they're actually probably happening at more or less at the same time. So the first process is the upward movement or relocation of uranium and thorium in the crust due to magmatic and hydrothermal processes associated with the collision between Gondwana and Northern Europe. And even uranium and thorium themselves, among themselves, are being redistributed in an organized way within the crust, because granitic liquids with high lanthanum and thorium will react with apatite in the crust and form monazite, which will incorporate thorium over uranium. And in this case, the thorium-uranium ratio will actually become a marker of the crustal level that we are looking at, such that the higher the thorium-uranium ratio, the deeper the crustal level we are looking at. And at the same time, lead is being concentrated in the lower crust in sulfide-rich cumulates. Lead is chalcophile, so it will just be mopped up by all of the sulfides. Okay, so you can see that we have these uranium and thorium and lead are being separated from each other and being reorganized within the crust. And now the thing is that we can actually lose the lower crust by crustal delamination, and if that happens, then we're using the big majority of lead in the crust into the mantle. Okay? And so the first process here is well known from Birch's heat flow, heat generation relationship, which we have known for a very long time, and which tells us that most of the uranium and thorium in the crust is concentrated in the upper 8 to 10 kilometers of the crust. And the process that controls lead is something which is very clearly evident by the very dramatic decrease of copper, which is another strongly chalcophile element in arc magmas upon arc magma differentiation. And so here I show you another map. This time it's from the literature, and this is a map that shows you the thickness of the continental crust across Europe in kilometers. And you can see how the crust is much thicker in Northern Europe than in Southern Europe, and it reminds you at a first order a little bit about the geochemical provinces that we have seen on our lead isotope maps. Now, crustal delamination has already been evoked to explain this difference in crustal thickness between Southern Europe and Northern Europe, and now our observation that we can see a correlation between the gradients in uranium lead and thorium lead with crustal thickness. Okay, this is strongly in support of the idea that the crust below Southern Europe was delaminated during the Variscan orogeny, and in this way we lost all of the lead into the mantle. And this is further supported by the observation of this little patch of crust in Finland, which is much thinner than all of the surrounding crust. And this little patch of thin crust also is characterized by high uranium lead and high thorium lead, whereas all the crust around it has low uranium lead and low thorium lead. And finally, this hypothesis would also be consistent with the gradient of thorium-uranium across Europe, because if we really lose the lower crust in bicrustal delamination, then we're going to have some isostatic readjustment, and the crust will rise, be followed by erosion, and we would have deeper levels of the crust exposed in Southern Europe compared with Northern Europe. So let me conclude on this first application before I move on to a couple of other applications in completely different fields. So I think that from what we have seen, lead isotopes actually are large-scale proxies of crustal differentiation and tectonics. They carry information about the first-order geodynamic processes that led to continent assembly and differentiation. Provided that isotopic information is read in the appropriate space of geochemically and geologically informed parameters, lead isotope geochemistry has the potential of discriminating physically coherent crustal units and revealing the geodynamic processes that led to the present geochemical identity. And what we were hoping, that the merging of multiple lead isotope datasets into one large, probably georeference database can, in fact, uncover new major large-scale geodynamic features that would otherwise have gone unnoticed. And so we hope that perhaps this idea can in the future be applied to some of the other continents and tectonic provinces elsewhere in the world. And so let me shift gears now and move into geoarcheology and show you how the lead isotope database can be used to tell us something about our ancient history. So that you don't, well, to keep this a little bit fun, I decided to focus on this very fascinating question about how lead poisoning might or might not have contributed to the decline of the Roman Empire. As I'm sure you all know, the Romans are famous for having made these very fancy water distribution systems throughout their empire, and all of their lead pipes, all of their lead pipes, right, was made from lead, right? And so the obvious question is that all the tap water, so to speak, all the drinking water that would be running through all of these lead pipes, would it be so contaminated by lead that it would actually, in the end, have poisoned the entire Roman society, so that they started to act irresponsible and make the wrong decisions, and finally the entire Roman Empire just collapsed? And so in order to look closer at that question, what we did was that we drilled sediment cores through all the historical layers of the Roman Empire in the harbor of ancient Rome, which is also known as the Trajanic Basin, which I'm showing you a picture of here. And we also sampled the lead pipes, which are called fistulae, and we measured then lead isotopes in all of these different sedimentary layers, and we measured the lead isotopes of the lead isotopic composition of the lead pipes. Now for me, this was kind of doing everything upside down, because what I usually do, I want to get the geological lead. So when I measure basalt, so when I measure meteorites, I will leach all of these, I will leach my samples to death so that I get rid of at least 90% of the lead, and then I hope that the last 10% has no anthropogenic contamination, and that the lead I am measuring is the original geological lead, or solar system lead, if you like. Well, in this case, what we really want here is the anthropogenic signal. So I had to come up with a completely different leaching procedure that would leach out all of the anthropogenic lead and leave behind all of the geological lead. So the lead isotopic compositions I'm talking about is all of the anthropogenic lead. And so here you have, again, to your left, kappa, so the model thorium-uranium ratio, plotted against the lead model ages on the x-axis. And to the other side, you have a much more standard geochemical or isotope diagram with a, in this case, it's a major element over a trace element ratio, and as a function of just a raw lead isotopic ratio. And on this diagram to your right, because the denominator is lead in both cases, any mixing relationship will show up as a straight line in this diagram. So there is a number of observations that we can make if we look first at the diagram to the left. So first of all, you can see that the fistulae, I can't really see it, but if I remember right, it's the green dots. You can see that if you project down to the x-axis scale, that the lead model ages for the lead that these lead pipes are made out of, they are 250 million years old, so this is Hercynian lead. So it means that the Romans used lead from Germany or France to build their their lead pipes. And this is contrary to everything that experts on ancient mines thought up until this point. They actually thought that the Romans were taking their lead from southern Spain, where the lead is incredibly young because it is associated with the Alpine collision. So this was the first surprise when we saw that. The second surprise, which was a really nice surprise, was that the anthropogenic component has the same lead isotopic composition as the lead pipes. And then you can see for all of the rest of the sediments, they just distribute themselves along a nice binary, beautiful mixing relationship between unpolluted type of water, which is what the Romans were drinking or draining into their water distribution system, and the end member anthropogenic component. And then with the help of the standard geochemist diagram to the right and our basic principle of mass balance, we could back out that the level of lead in Roman tap water was about 100 times above lead in the unpolluted type of water. So yes, for sure, the tap water that the Romans were drinking were definitely polluted in lead, but not enough by far to have caused the entire Roman society to collapse. So the answer to that is no. Another interesting thing is that here I just show you, to make it simple, the raw lead isotope ratios, but the transitions between units stand out even stronger when you use the geochemically informed parameters. And this is just down core in the sediment cores that we drilled into the Trajanic Basin, and you can see that the transitions between the different units are contemporaneous with historically documented events. And you can see how we start out at the bottom with the geological lead isotopic signature in red, and then we have the initial excavation of the Trajanic basement, and then we go up through the entire Roman Empire, the early, late Roman Empire, where the port isn't used, and we have some sort of steady state lead isotopic signal. And then we get to the Gothic Wars, and they reinforce the port, and we get a change in the lead isotopic composition. And then you get the reverse change after the Arabs have come and sacked Rome, and the port finally falls out of use, and it is the party is over, and we are going back into the red with the geological signature that comes back into these sediment cores. Of course, in order to do this, we need to have some good age depth models, and at the moment this is one of the weak points with doing this kind of science. We need to do that from carbon-14, and there are some other methods we can use as well, and this needs a lot more work. So let's move into archeometry, 2 examples of archeometry, and then you can go and have lunch. And I'll try to not be too long about this. It is self-regulating because I'm not very strong in history, so I will not be able to talk very much about that. But here we're going to have a focus on artifact provenancing and trade routes, a tale of war and greed. And what I'm showing you here is Isabel and Ferdinand's 4 reales silver coins after the Medina del Campo ordinance at the end of 1400. And so you need to know a little bit of Iberian geology to get the main point. And like I said earlier, like you could see from the previous maps that we have seen a lot of by now, Iberia is an old crustal segment, okay? But we have this little part of Iberia down in southwestern Iberia, which is very young, only 20 million years, compared with 300 to 500 million years for the rest of the Iberian Peninsula. And this came from the collision between Spain and Africa during the Alpine orogeny. And so there are silver mines in the Batics, and so there's always some lead in the silver, and so this lead is very young. So we have a very powerful tracer here for telling the difference between silver coming from something which is 300 to 500 million years old, and silver coming from something which is only 20 million years old, as you can see here. So the history behind that, the historical context, is that in the late 1480s, the Catholic kings attacked the Granada Emirate and seized Hannibal's silver mines. And so they immediately made new money with this new metal from the Batics. And you can see in yellow here, you can see all of the coins that were circulating already in the European monetary system at the time in yellow, made from from silver with much older lead model ages. And then you can see this very amazing peak here in turquoise from the new coins that was made immediately, more or less immediately, with much younger lead model ages. So the young ages of the Emirate clearly shows up in the lead used for coinage, and contrast with those from northern Spain and the rest of Europe. So this is a very instructive example of how lead model ages can be used for archeometry. And then I will finish with this last example, which is fresh or hot off the multi-collector ICP-MS over the last few weeks. We wanted to have it ready to show it to you here today. So we have just been plotting up these data in the last few days. And this time it is a story about devaluation and monetary reform. And what I'm showing you here is the Roman denarius before and after the monetary reform. There was a monetary reform from 2013 to 2011 BC. And a denarius in Latin means 1 day or 1 coin. And so a denarius was what a Roman soldier was paid per day for his service. And so the monetary reform is in between these two coin. So before, the coin weighed a lot more than after, but before, the silver that the coin was made from was impure, and after, it was much purer. So in a way, you can say that after, the soldiers would be paid by much purer silver, but of course, there is no silver lining. The weight of that silver was drastically taken down. So if you do the math, I am almost convinced that the soldier was never the winner of this game. So I have to admit that I had to pull out all my old asterisks in order to read up on Roman history in order to prepare this part of this talk. And here is the historical context that you need to know to understand the the silver and the lead isotope data that I will show you on the next and the last slide. First of all, the silver sources available to the Romans at the time was southern Spain, but that was under Punic occupation, Hannibal, the elephants, and all of that. But Baetic silver had been available to the Roman as war penalties from the mercenary war at around 240-238. So the Romans had some Baetic silver that they could make coins from before the monetary reform. And then there was Sardinia, which was under Roman occupation and available to the Roman, and finally Macedonia, but Macedonia at the time was a Punic ally. And so, like I said before, the Romans had been devaluating their silver money by adding copper to the silver. But in the long run, nobody wanted the impure silver coins of the Romans, and in the end, it caused the entire monetary system to collapse. And so that triggered the monetary reform, where the silver had to be cleaned up to become pure silver again. What you also need to know is that in 2016, before BC, the Romans were badly defeated in Lake Trasimene and Cannae by Hannibal and his elephants, and most of Italy was occupied by the Carthaginians. So this was not like a great, easy time for the Romans. And after the Romans had been defeated at Cannae, Syracuse became very brave all of a sudden and broke its treaty with Rome, but only to be retaken by the Romans after a long 2-year siege, and they were retaken in 2012. And it was during this time, by the way, that Archimedes was killed, supposedly while he was contemplating a very complicated mathematical diagram. And so in 2013 to 11, the monetary reform is taking place, and it consists of cleaning the copper-polluted silver with lead. This is the process we know as cupellation, and cutting down the daily silver coins of the denarius paid to the Roman silver to the Roman soldier from 6.3 to 3.7 grams. And the last thing you need to know is that in 2009, after the monetary reform, Scipio Africanus lands in Spain and eventually will defeat Hannibal. And so if you first look at the lead isotope data, which is the diagram to the right shown in the form of lead model ages, you're used to this now, then what is really surprising when we plotted up this data was how much the lead isotopes scatter. They're all over the place. And as you probably remember from a few slides ago, that if you have one source of silver, well, that will have one very specific lead isotopic composition, so the lead isotope data should not scatter all over the place. But they do, and so what this is telling us is that the Romans were forced to use scrap lead, basically whatever lead they happened to have lying around, in order to clean their silver, because their supply routes were cut off by the enemy at this time. And so the other thing which is surprising is now, if you look at the silver isotope data to the left, is this sharp change in silver isotopic composition during the monetary reform, which indicates that the source of the silver changed just at that time. And until we plotted up this data barely a week ago, nobody had any idea that the source of silver changed during the monetary reform. And as you can see, this change in the source of silver happens before Scipio lands in Spain and defeats Hannibal. So it has nothing to do with that. It's not because all of a sudden the Romans got the Baetic mines back. And in any case, our best guess is that the silver at around 220 is probably made from the Baetic silver that the Romans had available as war penalty. So we know what the silver isotopic composition looks like for the Baetic silver, and this is not what it looks like during and after the monetary reform. So that leaves Syracuse as the only source, as the only possibility for this new source of silver, because as you remember, Syracuse was taken back by the Romans in 2012, and this was accompanied by major spoils. And in fact, the taking of Syracuse was absolutely determinant for Roman victory and on the long run. So if I conclude on this last part, of this talk, and after that you will be free to go, then lead isotope systematics of sediment cores taken from ancient cities and harbors or ports. And we're actually doing that in many old ports around the entire Mediterranean at this point in collaboration with geoarchaeologists. Add a new dimension to the understanding of the environment of these ports and the major changes that affected them. And but like I said earlier, to make this work even more important, a major effort is now needed to refine the chronology of sediment cores so that breaks in the paleoenvironmental record can be related to recorded, but also even unrecorded events, such as wars, invasions, earthquakes, floods, and major diseases. And finally, as I hope to have shown you here in the last couple of two examples, isotopic data on silver coins bring to light new information on the manufacturing status of ancient cultures and the trade routes through which they connected, as well as the impact of war. And I would like to, of course, thank all my collaborators on the various aspects of the work that I've been showing you during this talk, and I would like to thank all of you for your patience today and for being here in the first place.
Thank you very much, Janne, for this excellent talk. We just checked with the president, because your stomachs are already growling so loud, you are released, and you can follow Janne for asking her more questions about her fantastic talk. Thanks very much, Janne.
Thank you.